Hello, folks. Okay, I want to go through some finite state machine examples here. I think finite state machines tend to make more sense once you see them in action and run through a few examples. If you're perfectly comfortable with finite automata and finite state machines and whatnot, then feel free to skip these. But if you're a little rusty or a little unsure on how to create these things, we'll just spend a few minutes going through a few examples. Let's see, where did we want to start? Let's look at one where the alphabet that we're going to work with are just zeros and ones. So we've got strings of zeros and ones, and we're going to assume they represent, binary numbers. And what we're looking for are strings that represent positive binary numbers, so bigger than zero, that are even. So essentially that means it's got to end in a zero, and there's got to be at least one 1 in there someplace, right? To get it bigger than zero, we need a 1 in there someplace, and for it to be even, we need it to end in a 0. So the biggest trick is always thinking about, okay, well, what are my states going to represent? Well, I might have my start state that's saying, well, all I've seen so far is 0, right? I don't have anything that is bigger than 1 yet. As soon as I see a 1, I can say, well, whatever number it is I'm reading in, it's bigger than 1 already, or it's bigger than 0 already. So at that point, I've got half the battle solved. And eventually it means I've got to see a 0 to end this thing. So if we think of things through, we'll say, okay, well, I'll start off, so S0 is my start state. As long as I keep seeing zeros, I'll just stay here waiting for something that tells me it's bigger than 0. I see a 1 and go, okay, I've seen at least one 1. I can see as many more 1s as I like, and it's still going to be bigger than 0. And if I see a 0, I'm going to say, so far it looks valid, right? It's bigger than 0, it ends in a 0, it looks okay. And as long as I keep seeing zeros, right, it's still an even number. If I keep adding zeros, I'm essentially multiplying by 2, so it's staying even. If I ever see a 1, then I can say, it no longer ends in a 0, so I'm back here waiting for another 0, so it's okay again. So you just get this cycle going of, if I see a 0, okay, it looks good, and I can keep seeing zeros. If I ever see a 1, it's like, okay, I've got to go back and, if I see a bunch more 1s, I'm just sitting around waiting for a 0. So this is going to be the cycle that I'm looking at. Now, for these, again, we've got the start state denoted typically with an arrow in, the accept state indicated with the circle with a circle inside it. And I'm going to assume that any of the transitions that I don't show here, so if there's, if we had an alphabet that was bigger than this, if there's any arrows that are left off, then I'm assuming that they're going to go off to kind of just a generic reject state, just to keep these things simple. It doesn't matter with this particular finite state machine, but with some of the others, it's going to make a difference. So, example number 1. Let's take a look at another one. And in this case, our alphabet is going to be ABC, so we're looking at strings that contain A's and B's and C's. And what we're interested in are the ones where the number of B's is a multiple of 3. So 0 B's, 3 B's, 6 B's, 9 B's, that kind of thing. They can be anywhere in the string, and we don't care how many A's and C's are scattered around in between. All we're interested in is whether or not the total number of B's is divisible by 3. So again, the big trick is coming up with what should my states represent. And if I'm looking at a number of B's that's divisible by 3, then keeping track of the remainder is fairly useful. If I say, well, if I take the number of B's, divide it by 3, and look at the remainder, if it's 0, then it's an accept state, it's evenly divisible by 3. If it's 1, then I need to see 2 more B's before it's valid again. And if the remainder is 2, I need to see 1 more B before it's a valid string again, as far as we're concerned. So I'll have my 3 states that reflect the remainder after dividing the number of B's by 3 and taking the remainder. Right? So a remainder of 0, a remainder of 1, and a remainder of 2. So as far as my machine is concerned, if I'm in that start state, I'm in an accept state. The number of B's is 0 so far, and that's evenly divisible by 3. I don't care about A's and C's. If I see A's and C's, I just stick right in my start state, my accept state here. If I see a B, now I've got a remainder of 1. And if I keep seeing A's and C's, I've still got a remainder of 1, right? If I see another B, I've got a remainder of 2. And if I keep seeing A's and C's, I've still got a remainder of 2. And then if I see one more B, Now I've got a number that's divisible by 3, and I'll go back to my accept state. Right? So you just get this nice cycle where you're going through and saying, okay, well, how many b's do I have left over after dividing by 3? And again, any states not listed would have gone to a reject. All right, let's try another one. How about a simple representation for fixed point or fixed floating point numbers? Right, so what I'm expecting here, we'll keep it fairly simple, is it's got to be one or more digits, and then there's got to be a decimal place, and then there's got to be one or more digits afterwards. So my states will reflect how much of that I've seen so far. Have a state for I haven't seen anything yet. Have a state for I've seen some digits, but I haven't seen the decimal point yet. Have a state for I've seen the decimal point, but I haven't seen those last set of digits yet. And have a state for, oh, hey, great, wonderful, I've seen that last set of digits. So my start state, if I see a digit, right, a 0, 1, 2, 3, etc., then I go to my start, or my next state, where I'm saying, okay, well, I've seen at least one digit, and if I keep seeing digits, it still looks valid, but I haven't seen my decimal point yet. I see a decimal point, and I go, okay, I've seen my decimal point, but I haven't seen the last set of digits yet. I see a digit, and I go, okay, it looks like it's a valid, this is 123.7 or something. It looks valid. But I might be seeing more digits, right? There still might be more to come, so we'll keep accepting them as long as they're there. And again, if the alphabet had other characters in it, then any of those others would take us off to a reject state. Or if I saw an extra dot, or if I didn't see any dot, we wind up ending in a reject state, or a non-accepting state. All right, and just do one more example. And this one's going to be back to a divisible by 3 type of approach. But for this one, I'm going to say I'm going to have binary integers, so just zeros and ones. We'll assume that it's unsigned, so we're not worried about 2's complement or anything like that. But I want the numbers that are represented to be evenly divisible by 3. So things like 1, 1, right, representing 3, or 1, 1, 0 for 6, or 1, 0, 0, 1 for 9, right? That kind of idea to represent the binary numbers evenly divisible by 3. So in this case, again, my states are going to represent the remainder after dividing the represented number by 3. So remainder of 0, remainder of 1, remainder of 2, where the remainder of 0 is valid. So I just have to come up with a suitable scheme for figuring out if I've got a remainder of 0 so far and I stick a 1 on the end, what's that going to mean for my remainder for that new number? Or if I've got a remainder of 2 so far and I stick a 0 on the end, what's that going to mean for the remainder in the new number? And again, we can sit down and reason that out. So right now, if I've got a remainder of 0, that means n mod 3 is 0, so that means that there's some x, so that n equals 3 times x, right? There's some integer x. So if I double n, then I'm essentially doubling my 3x. So if I add a 0 on the end, right, if I've got a binary number so far and I stick a 0 on the end, that's effectively multiplying it by 2. So it's giving me 2n, so 6x. That's still going to be divisible by 3. So I'm still going to wind up with a remainder of 0. So that one's nice and easy. If I'm in my state 0 and I stick a 0 on the end, I'm still in state 0. If I stuck a 1 on the end, then that's like multiplying the number by 2 and then adding 1. Right? So I'm going to 2n plus 1, so that's going to be, if n was 3x, that's going to give me 6x plus 1, which means I'm going to have a remainder of 1. So that's the state I go to. And we follow that same sort of logic for the other cases. If n mod 3 is 1, then n is equal to 3x plus 1 for some integer x. So if I stick a 0 on the end, I'm doubling that, so I'm getting 6x plus 2, so I'm going to wind up with a remainder of 2. If I stick a 1 on the end of it, it's giving me 2n plus 1, so that's giving me, so if I double this, well, essentially I'm taking my 6x plus 2 and adding 1, right? So I'm getting my 6x plus 3, that's going to give me my remainder 0 again, right? Because now I've got, again, a number that's divisible by 3. And same sort of idea. If n mod 3 is 2, then n is 3x plus 2 for some x. If I stick a 0 on the end, I'm doubling that, so I'm getting 6x plus 4. which is going to give me a remainder of 1 when I divide by 3. If I take my n and stick a 1 on the end of it, I'm doubling it and adding 1, so I'm getting 6x plus 5 essentially, which is going to give me my remainder 2. So that gives us a way to go through and figure out what our transitions between the states are. If I've got a remainder of 0 and I add a 1, I'm going to have a remainder of 2 on the new number. If I've got a remainder of 0 so far and I stick a 0 on the end, the new number is still going to have a remainder of 0, etc., etc., etc. So we can sketch out, right? As long as you can come up with a rational set of states to represent the condition that you're working with right now, and you can come up with transitions that say, okay, well, if this is the condition I've got so far, and I add a this letter on the end, what does that do to me in terms of which state I should be in next? Right? That's the kind of logic that we're looking for. All right, I think that will do us for now. We'll go back to looking at our algorithms next time around.